Hey there. Um, this is a video where we're going to take a look at using the ratio test to establish convergence or divergence of infinite series. So a quick synopsis of what we're going to have in mind there, which is that we're going to have a series. I should probably have written summation n equals 1 to infinity a sub n over here. The a sub n this time could include a minus 1 to the n. It could include anything, okay? But this ratio test stuff is specifically designed to detect things that work like geometric series or things that work like factorials, okay? And it can specifically handle things along those lines that aren't exactly the same, okay? So the things it cannot handle, it cannot do anything that looks like a p-series. Anything that looks like logarithms, this just will not be helpful on, okay? So in any case, if you have your series here and the formulas for the terms written out, you have to figure out how to write what a sub n plus 1 is. So if I look down here, if I said a sub n was equal to, let's say 1 over 2n plus 3, okay? Then when I do a sub n plus 1, that means replace all of the n's with n plus 1's, and then do whatever algebra is necessary to finish that up. And here that ends up going 2n plus 5, okay? If, however, my a sub n was, let's say, 1 over 2n factorial, okay? As a matter of fact, I am going to jazz that up a little bit. I'm going to say 3n factorial, okay? So you all know that if I were talking about n factorial, that is 1 times 2 times 3 on up to n. And if I said n plus 1 factorial, I would need the parentheses, because otherwise, if you ask a computer to do it, it will just take the factorial of the 1. But that would be 1 times 2 times 3 times on up to n plus 1. And because of how we usually work with these, I always go ahead and write the last 2 terms of it, okay? So it might have behooved me on this one to write n minus 1 and n as the last couple of things. So if here you had this a sub n plus 1, and you know that that needs to be 1 over 3n plus 3 factorial, then you need to be able to spot that that is going to have 1 times 2 times on up to the 3n. Oh, that is too small. I'm sorry, folks. Let me just erase that and put it on a different line. So 1 times 2 times and on up to the 3n, but also the 3n plus 1, the 3n plus 2, and the 3n plus 3, okay? So when you had that plus 1 on this, it actually added 3 terms because it's got to get all the stuff that's in between, okay? So factorials are a little bit tricky, but this particular test is going to make stuff that we're doing with them a little bit easier to mess with, all right? So let's take a look at an example that you actually did a different way a couple of days ago. All right. So this ratio test example has us dealing with the series summation of n divided by 2 to the n. Now, as you'll recall, you can totally get that by limit comparison test, okay? But it's tricky to do by limit comparison test. It turns out that it's super easy to do by ratio test though, okay? So if we've got n divided by 2 to the n, we will just put a copy of that into the denominator. That part's always easy. The numerator has a little bit more trickiness to it. The n becomes n plus 1, and then 2 to the n becomes 2 to the n plus 1. Make sure you understand the algebra of that. 2 to the n plus 1 is not the same as 2 to the n plus 1. And if that confused you, I'm sorry. But in any case, with regard to this, everything you're doing is positive. So those absolute value signs in there, those didn't actually help us this time around. But sometimes we'll have problems where there's a minus 1 to the n, and that absolute value just wipes it out, okay? So we can just drop them this time, and with simplifying, we will end up with an n over n plus 1 from the two numerators, and then a 2 to the n over 2 to the n plus 1. So in the limit, the n plus 1 over n will turn out to be 1. If we had not taken the limit yet, it wouldn't be equal to 1, okay? But before taking the limit, you could actually cancel on these and have just 1/2. And then in the limit, the 1/2 is still a 1/2. So you end up with 1 times 1/2, which is a number less than 1. So if that limit that you got was less than 1, ratio test said convergence. Boom, done. Okay. So that tells us that this series here converges. And more than that, the ratio test lets you know something is absolutely convergent because it took the absolute value of it in there. But if it's a positive sum of positive terms, absolute convergence and convergence are the same thing. You only need to say absolutely if you're talking about an alternating series. Okay. All right. So let's take a look at another one here. And that would be something from the wrong day. Okay, ratio test. So this one is tricky because of the way it's written. You have to be able to look at it and see how that numerator is working in this one here. Because it says 1 times 3 times 5 times ... up to 2n plus 1. So that tells you it is only taking odd numbers. It has canceled out the even numbers. If you really love formulas and you want to have a formula for that doesn't have a ... in it, just ask me sometime and I'll write it out. I would like to say it's not hard to do, but it is hard to do. So I'm going to just deal with it more in the intuitive sense right now. So we've got that idea in mind of what the a sub n's look like. So when you say a sub n plus 1, and you substitute n plus 1 in for n, then you end up with a 2n plus 3. So it's all the odd numbers up to 2n plus 3. So here, I went ahead and wrote this down. Remember that the denominator down here is just a copy of your original series terms. Then your numerator up here is going to be what you get when you go one term further. So because we're talking about factorials or factorial-like things, you'll get an extra term on it. So coming down here and putting the two numerators together, that numerator from the one with the n plus 1 is going to go 1, 3, 5, ... and it will include the 2n plus 1, but it will also, of course, include the 2n plus 3. So it is the same thing and then one more. So then the n factorial and the n plus 1 factorial, we just have to get them put in the right place, okay? And we have to remember that for this, we mostly want to do cancellations of the same things and see what's left over. And then here with the n factorial, when you cancel that against the n plus 1 factorial, you're only left with that one remaining term at the end. So that's why this down here turns into the 2n plus 3 divided by the n plus 1. And of course, taking the limit as n goes to infinity, you know that in doing those, since they're the same power, you just divide the corresponding highest power coefficients, and we end up with 2 in the limit, right? 2 is more than 1, and that tells me that this summation must actually diverge. I forgot to write by the ratio test, but that's what we're doing on that there, okay? So frequently as I'm doing these, I really want to turn to you and say, are there any questions? Because it would be nice to be doing this in the classroom instead of doing it all online. Sorry. But let's look at one more example here, and I have to get the right example because I've got too much stuff saved on my iPad already. So one more example here, and this, I always try to save a tough one for the end, okay? So this one has n factorial divided by n to the n. Now, I've mentioned to y'all before, I've used the word before that we have something called tetrations that are the n to the n power. You could also have n to the n, then to the n power, and those end up growing like really, really fast. If you want to know more about those, Google something called up arrow notation. The only application I know of it is in scoring points in Magic the Gathering. So, all right. In any case, though, we've got this series here that has the n factorial divided by n to the n. N factorial grows really fast, but n to the n grows even faster. So the question is whether it grows enough faster to make this go to 0 fast enough. That's not well phrased. Whether the ratio between them still goes, or still creates something whose summation converges. So, of course, the a sub n's we identify out here, and that part's no problem. But the a sub n plus 1s, we have to be a little careful with. We get an n plus 1 factorial, but we also have an n plus 1 parentheses to the n plus 1 power. Oof, yuck. It's kind of messy. All right, then when we set up our limit here, we have the top with that n plus 1 factorial and the n plus 1 to the n plus 1. And everything we're dealing with is positive, so we can drop the absolute values. If you had a minus 1 to the n and you drop the absolute values, you'd be in trouble. But here we don't have one. So then simplifying, I have the n plus 1 factorial divided by the n factorial, which you all know everything except the last term will cancel out. The other part, no such luck, right? Man. But when we simplify down here, then we have an n plus 1 sitting here, that would actually cancel against one of the n plus ones that's sitting there. Then that means that we cancel this and one of those, and now we have n over n plus 1 to the nth power, okay? Now, that is of the 1 to the infinity form. Hopefully you remember that that's a L'Hopital's rule sort of thing, but it's not a super easy L'Hopital's rule, okay? That limit, when you break the fraction apart like that, seeing that minus 1 over n plus 1 there, if you've seen it before, you'll go, oh, right, that's going to turn out to be e to the negative 1, okay? But if you haven't done that one recently, you might have to think about, well, if I took the logarithm of that term there, then that would pull the n out to the front, and then I could rewrite that with a division problem and have the log divided by 1 over n. That is completely counterintuitive. But the reason that you need to be able to do that is so that your top goes to 0 and your bottom also goes to 0, okay? That's your setup to say that you have L'Hopital's rule ready to go. So you hit it with L'Hopital's rule. The stuff in the denominator is easy. Derivative 1 over n is negative 1 over n squared. But the stuff in the numerator is not easy. You have 1 over the stuff that you were taking the log of, but then the chain rule says you have to take the derivative of what was inside the parentheses. And if you remember, inside the parentheses here, you had a 1, and its derivative is going to be 0. But the derivative of negative 1 over n plus 1 is going to get you another negative. So that means we have a negative negative 1. That's why we don't have any negatives down here. But the power goes from being negative 1 to being negative 2, which means you have 1 over n plus 1 squared. Okay. Ugh. So if you do a little simplifying the algebra, notice that we have the negative coming from the denominator still hanging on. And then we can put the first part together and have this n squared and n plus 1 squared. Same powers. So when we go to infinity, we just divide the coefficients of the highest powers, the n squares, and we get 1. And then this other piece here has 1 over 1 minus 1 over n plus 1. Messy. But this bit here goes to 0, and that tells you that this bit here turns out to be 1. Okay? So that means our final limit is negative 1, but that final limit was the logarithm of what we wanted. So we have to exponentiate, and that's where we get the e to the minus 1. Okay? So where was that? Way up here. Okay, so this e to the minus 1 is less than 1. Okay? So, oof. To draw a really long arrow here. All right. And thus, summation n equals 1 to infinity, n factorial over n to the n converges by ratio test. All right. So I will actually upload a PDF of that particular exercise there for you to read through, because that is about the hardest one that we usually do as an example in calculus. It's just painful. you know, because it's got all those little details to it. But it's also good because you see all this stuff tying together. L'Hopital's rule, factorials, ratio test, etc. It's good to know how to do all this stuff. So, all right, that gets us for ratio test, and next up we're going to be talking about root test, and I will see you then.